All right. Hello there. This will be CS 471, 571 operating systems. And for this video, I want to kind of give an overview of what the plan is, what's an operating system supposed to do, and start getting into things. If you're watching this video, you know where the videos are kept, and I'll also be trying to take some notes in some slides. So if I was normally going to draw something on the board, we'll put it over here so that we'll have this to look at. And we're going to be looking in the textbook/notes for xv6, and that's an important enough link that we're going to put that up at the top here. All right. And I'll kind of take some notes here as well as we go. All right, so I want to say this. This is where we start. What is an operating system supposed to do? And there's two main things. You could probably come up with a few more main things, but this is my view of things. So one thing an operating system is supposed to do is make it easy to write programs. We want our programs to be in a high-level language. We don't want to have to deal with the exact way to interface with a particular kind of hard drive and so forth. All right, so all that messiness of dealing with the actual hardware, the operating system helps abstract so that we can have a programming interface that's easier to use. All right, and the other main thing that an operating system does is enable multiple programs to be running simultaneously or in sequence on the same system to share the resources and protect them from each other. All right, so most of what we're going to do in this class has to do with one or the other or both of these goals. Okay, a note that's important that we'll see at some point is the physical hardware matters. So what kind of CPU an operating system is written for, it makes a difference. And so some of the things that we want to do in the operating system, if we don't have the right features available on the CPU, it'll either be difficult to do or not possible. And we'll see examples of that, where this is a really awesome operating system idea, and it started being standard in an operating system once the CPU started to include a particular instruction that was needed. All right. In our class, we're sort of thinking of the operating system as managing three primary resources. We have the CPU, memory, and storage. And for each of those, there are some abstractions that the operating system provides to the programs. So for the CPU, the main abstraction is the process. So a process is a running program. That means the state of the CPU, and memory as the program runs, and whatever other resources the process is using, so open files. What the operating system will do is when it's time for one program to stop and another program to start, all of that has to be saved somewhere so that then your process that's being stopped can be started again at some point, and that's called a context switch. All right. Another of the three main resources is memory, and one of the abstractions here is the concept of virtual memory, which we will see how that works. So with virtual memory, each process can think it has its own private copy of memory. Okay, so the process doesn't have to worry about where in real physical memory the other processes are. The abstraction will be that as a process, I think what it looks like to me when I try to access memory, it looks like it's all mine. And I don't have to worry about the other programs. And one of the key mechanisms for realizing this is the concept of a page of memory, so a chunk or a block of memory. And each chunk or block of physical memory can belong to some particular process, can have certain access rights. And then the fact that we want to break memory up into chunks or pages will lead to how memory is organized in the operating system to make this work. All right, our third piece of hardware that we're managing as the operating system is storage, so a hard disk drive or a solid state drive, long-term storage. And the main abstraction here is the file system, which we normally think of as a tree-based directory structure. So you start at the root directory, you can go through directories and find files and things. So that's an abstraction. That's not the raw interface to the drive is writing bytes to particular positions on the drive. This file system tree-based structure is something that the operating system provides. Okay, so there you go. There's some concepts in operating systems, boring listening to me. So now just maybe take a pause. See if you want to read any of that. I'll even take a pause. All right, and now I want to start talking about xv6. So xv6 is, it's a developed by at MIT, some part of the Unix 6. So the interface is some part of the Unix System 6, and so they basically took Unix System 6 and make a version of it that we have all the code. It's easy to use for teaching and stuff like that. So basically it's basically a simple version of Unix. Okay, that's used for teaching at MIT and lots of other places. So we're in very good company for looking at this xv6. All right, so the link here to the textbook / notes about xv6 is, so it's something like, I don't know, 100 pages or something, and then it's broken up into, is there a table of contents? So it's broken up into basically descriptions of the abstractions that the xv6 system provides and how that's all done. It starts off in the first chapter that has index 0, of course, talking about the interface that the operating system provides. And I want to take, I'll put some kind of notes or a picture over here about what things look like based on this. So if we're a process, if we're writing a C program to use to run in xv6, what does it look like the operating system is doing for us? Okay, so this chapter you should read, but I'm going to skip to a list of the system calls. A system call is a part of this is actual operating system code. Each of these system calls is operating system code. So the code to write this fork is part of xv6. As a program that's running on xv6, I don't get to control what this code looks like. That's the operating system. All right, so this is the set of system calls that are provided for us in xv6. They're the important ones, the most important ones. There are many others in current versions of Linux or Unix, but these are enough to see a lot of the main ideas about what's going on in the operating system. Okay, so I'm going to pick out a few of these system calls and just discuss what that means for us in terms of what the operating system looks like. I'm going to start with, let's see, these first ones are the ones fork exec, wait, kill, get PID, sleep, exec. Those are all related to process management. What fork does is it splits a program into two identical copies that then are both running. So if I was going to, let's see, we'll just draw some pictures here. Let's go like this. So a fork system call, you've got a process 1, which has a CPU state. It has memory state. It has open files, right? So after a call to fork, you now have two processes that have the identical, put a box around that. All right, so nearly identical everything. So the only difference is, so let's say that this one is the parent. One of them will be the parent and one of them will be the child. And the way that that is decided is there is a, if we look over here at fork, it's a system call that returns a value. So it'll return a value that says which one of them is going to be the parent and the child. So PID returned by fork is PID of child. Okay, and then over here, the PID returned by fork is 0. So if you have a program and you call fork, then if you get a 0 returned by the call to fork, you're the child, and if you get something else, you're the parent. Okay, that's what fork does. What do these other ones do? Exit closes a process, wait waits for a process, for some child process to be done, and you guys are all working on this right now, so you maybe know this stuff. So in the parent there, you could call a wait on the PID of the child and wait for it to finish, wait for it to exit. Get PID gets the current process's PID. All right, so I want to make keep some notes up here of what things look like. So what has to be in the operating system based on the system calls. So I'm going to, let's see, put something here. So inside the operating system somewhere, there has to be a list of processes. Right over here, we have multiple processes. The processes have process IDs that are all unique. So there are some list of processes. So that could be, it could be kept in just an array or some other data structure. And each process has CPU state, memory state, open files. Okay, so you could imagine writing a process, let's see, you could store that information in a structure, right? Some kind of C structure that has room for the CPU state, the memory state, and open files. Okay, so somewhere inside of the operating system, there is a list of processes. It's an array or something. And we could start to imagine what that data structure might look like. Okay, we could also keep track here of hardware, what it must provide based on this. And we'll make a bulleted list. So it has to have a way to do context switching. We're going to have multiple different processes running on the same CPU. There has to be a way to switch. If we have the CPU state, we want to switch back to that, there's some way to do that. So there's going to be some instruction in our whatever CPU we're using that can do this context switch. Okay, let's look through. So there's some here: open, read, write, close, dupe, pipe. These all have to do with files. The Unix operating system has a concept of a file descriptor, which uniquely identifies some file in the file system. Okay, so there is some list of file descriptors. Those are open files from the file system. So this could be also, so it could store the file descriptors, file information in an array, and use the array index as a file descriptor. That would be a first attempt at keeping track of files. So if we open a file, that's going to return a file descriptor, which is supposed to be a unique identifier that identifies an open file. With that file descriptor, we can read, we can write, we could make a new copy of that open file descriptor, we could do a pipe. Okay, so note, list of file descriptors is kept for each process. So each process has its own list of file descriptors. So this array here of information about files that are open, that would be in this process data structure. Okay, so for each process, the operating system has to keep some information for that process. All right, then we have some system calls to do directories, so things with directories. So we have a concept of a directory. So the operating system has to provide something with directories, which are really files that contain a list of other files. And that's what a directory does. And it's also providing this concept of a link to a file. So file links, which is a way to have, let's see, I'm in my downloads directory here on my Mac, which is a Unix computer. There's a file here called transcript.pdf. I could make a link all right, so now I have something called new PDF. If I wanted to open new PDF, I won't because it's somebody's transcript. But I could call on my Mac here open new.pdf, and it would actually go and open transcript.pdf. So those are both entries in my directory, my list of things for this directory. They really point to the same physical file. And the Unix system provides this concept of links, where you can have two different names for the same file. They could be in different directories even. I could move this into my, say, documents if I look at my documents, so there's something called new.pdf there, and it kept track that it's actually pointing over to this transcript in my downloads directory. All right, so the operating system has to do that. So file links, I'll just say that like that, and maybe we'll add to that at a later time. All right, let me pause. So you can pause, I can pause. Okay, I think that's enough for this video. The plan is you should be reading through this information. So first chapter here is it's just talking about what the operating system provides. So what we're going to do next, so this is the video that we're doing right now. So the next video that will be in progress will be working with code in xv6. So we're going to have this set up on the CS server so that we can run this operating system in a operating system emulator in a virtual machine. And so we'll be looking at how to get that going, in particular writing utilities that use the xv6 system calls. Okay, so we're going to make programs, so just C programs, but they're not going to be compiled for Linux, they're going to be compiled for xv6. All right, so that's where we'll go, and then coming up soon, so working with xv6, first we do utilities. Along the way, key Unix OS concepts. Eventually, we have some quizzes about the key Unix OS concepts. But first, I think we want to get into writing some code there. And we'll keep notes along the way. All right, so we can keep notes over here about what the world looks like, and also up here about things we're supposed to know. So there's terms here that will probably grow as I say things. All right, that's it for now. Have fun.